We're back talking about velocity and acceleration and the motion of particles. We're going to focus more today on the graphing, the visual of how motion works, as opposed to just looking at the theoretical problems, like the actual equations themselves. We're going to do it from a visual sense today. So we'll be looking more at velocity graphs and seeing how we can learn to interpret those. So we're going to start, before we do a velocity graph, we're going to start with a position graph. Now from a position graph, you can always tell velocity. So how can you tell the velocity from a position graph? Well, the velocity is the derivative of the position. Therefore, and the word derivative is synonymous to slope, so the velocity would be the slope of the position graph. And so I've broken this graph up into several time intervals, and we want to look at the slope of the different pieces. So we're going to start with the interval -3 to -2, which is this piece here. And the velocity of that would be the derivative of that section, which would be the slope of that section. And the slope of that section is 1. Then we move on to the next interval from -2 to -1. That has a different derivative because it has a different slope, so it will have a different value for the velocity, and that velocity value would be -1. So would the next interval also have a value of -1, and so would the interval from 0 to 1 also have a value of -1. The next interval from 1 to 2 has a different slope, so it has a different velocity value. And since the slope is 0, the velocity in that section is 0. Then we move to the section from 2 to 3. It has a different slope, and so the slope value is up 2 over 1, and so the velocity is 2. And then from 3 to 4, the velocity continues to be 2. From 4 to 5, my slope is 0, so my velocity is 0. And remember, every time velocity is 0, the particle is at rest. And then from 5 to 6, we have a negative slope, -1, and also from 6 to 7. So that's reading a position graph from which you can always tell the velocity. So I've transferred those numbers onto our next screen. Now, how do we draw the velocity graph, and also how do we draw the speed graph? Drawing a velocity graph is drawing a discontinuous derivative graph. And so the drawing of it, I'm just going to overlap. I'm going to do it in red. So between the interval -3 to -2, having a velocity of 1 would have a closed circle to an open circle. The open circle indicates that there is a corner there where I'm changing to a different velocity. All these intervals from -2 to 1 all have a velocity value of -1, so that would be a horizontal piece that would correspond that long. From 1 to 2, I have a velocity value of 0, so I'll be right on the x-axis. From 2 to 3 and 3 to 4, I have a velocity value of 2, so I'll jump up to 2 and I will have a velocity graph, a velocity piece up that high. Then I have another place where it's at rest from 4 to 5. And then I've got another section again, 2 intervals in a row, where it's -1 up until the end. So that is the drawing of the velocity graph superimposed upon the original graph. Now, how do I make it a speed graph? Well, speed is the absolute value of velocity. And so my pieces of velocity that were already positive stay positive. There's no change in those. And the pieces that were already zero stay zero. But the pieces of the velocity graph that were negative will now become positive. And so that open circle will overlap the other open circle. Still open though. Okay, it's not a closed circle, but an open circle because of the corner. And then again, this piece moving up to being a positive section. So the negative sections move to positive. So this is the graph of the velocity superimposed on top of the position graph we started with, and this is a graph of the speed superimposed also on top of the position. Okay, now we're going to be looking at a velocity graph, and using the same technique, if we look at a velocity graph, we should be able to determine the acceleration, because the acceleration is the derivative of the velocity. And so if I'm looking at the velocity graph itself, I can figure out what the acceleration is. All right, I've added a second line for acceleration onto this graph here. This is a different shape than what we were looking at before. When you're looking at a velocity graph itself, the first thing you want to do with the intervals is for velocity, you just want to put whether it's above or below the x-axis. And so from 3 to 2 here, my section of the graph is below the x-axis, so I'm going to put a negative. Its slope, which translates to its derivative, which translates to acceleration, is -1. The next section, from -2 to -1, is also below the x-axis, but its slope is positive, and so I now have +1. The next section, from 1 to 2, has now moved to be above the x-axis, so I'm going to put a plus there, but its slope continues to be +1. From 0 to 1 is also above the x-axis, and its slope continues to be +1. From 1 to 2, its slope, or its values, are above the x-axis, so it's a positive, but its slope is 0. From 2 to 3, its slope is, or its value is above the x-axis, but its slope is -2. Then from 3 to 4, let me change. We drop below the x-axis, and its slope continues to be -2. From 4 to 5, we're below the x-axis with a slope of 0. From 5 to 6, we are below the x-axis with a slope of 1. And from 6 to 7, we are below the x-axis with a slope of 1. So when you're doing two things at the same time, velocity and acceleration itself, you're looking for, when you're looking at the graph itself, velocity is the graph, you're just going to indicate pluses and minuses. What this does is it helps us with the intermediate value theorem. So let's think back about that. The intermediate value theorem required things to be continuous. This graph is continuous, okay? Also, the intermediate value theorem said to look for places where you could find negative values changing to positive values, or positive values changing to negative values. And that's happening a couple times on our graph. It happens right here, where I'm changing from a negative to a positive. And then it happens again right here, where I change from a positive to a negative. There are 2 times where this graph showed a change, and because it's continuous, you can't change from positive to negative or negative to positive without being 0 at some point. And so that indicates that's where the 0 is, to show at rest. And then also right here, at rest. So I can tell that this function is at rest twice. It's at rest at -1, where it crossed the x-axis. It's at rest again at 3, where it crossed the x-axis. It would have been at rest at the beginning, before it got started, of course, and it would have been at rest at the end, again, when it returned back to the origin, but it's at rest 3 different times. Okay, on the next screen, I've translated all of these over, and I've turned them all into pluses or minuses or zeros. So the question is, when does the particle change direction? Well, we've kind of already identified that. It changed direction from here to here. Okay? It's changing because it had negative velocity changing to positive velocity. It also changed direction between those 2 intervals, changing from positive velocity to negative velocity. So the particle changes direction twice. And we say it's changes direction at time equals -1, because v of t changes from negative to positive, and also at t equals 3. And that is because the velocity changes from positive to negative. A change in direction is always associated with a change of sign in the velocity. When is the particle going to the right? Well, as long as there's a plus sign, the particle is going to the right. So I'm going to look for everywhere that I'm going to the right. So this whole section, all of these intervals, the particle is going to the right. So we say from -1 all the way to 2, so we combine all those intervals together, the particle is going right because of those plus signs, because the velocity is greater than 0. The velocity is positive. Well, when is it going to the left? Well, anytime I would have negative values, the particle is going to the left. So from -3 to t and up to -1, and again from 3 all the way up to 7, the particle is going left because, and then for the opposite reason, v of t is less than 0. And then the final question, when is it stopped? Oh, you know what? I just realized, you guys probably already saw it, that I did not circle all the positive ones. There we go. Okay, now I've covered it all. So let's fix that. Going to the right all the way until 3. All right, so if we'd been in Zoom class, I'm sure you would have stopped me at that point. Okay, now when is it stopped? Well, we've already determined when it was stopped. It's when it's changing from one to the other according to the intermediate value theorem. And so we'll finish this by the IVT. Since v of t is continuous, the particle must have v of t equal to 0, which is what it means to be at rest, at both t equals -1 and t equals +3. So notice everything, the because always has to do with the velocity. Because v of t is greater than 0. Because v of t is less than 0. Because v of t is changing, I'm out of room, nature. Okay, one of them is changing from negative to positive, and the other it's changing from positive to negative. Okay, we can tell all of that. Now, what about the acceleration? What can we learn from that? Well, okay, here's the same chart. When is the particle speeding up? When is the particle slowing down? Remember, we defined speeding up as when velocity and acceleration have opposite signs as each other. And so for speeding up, I'm going to do green. Okay, speeding up will be green. I see that the velocity and the acceleration are opposite in the interval -2 to -1. I see again that they are opposite in the interval 2 to 3. And then they again are opposite in this whole interval. So the particle speeds up in -2 to -1, 2 to 3, and 5 to 7, because v of t and a of t, oh goodness, oh, I am just zoomed out, aren't I? I just did the slowing down section. Oh my word. Okay, well, we're not going to re-record. If I was going for perfection, I would re-record. All right, we'll just switch it. Good thing I'm in Notability and I can erase things. So let's answer the slowing down question first. The particle slows down. Okay, they have opposite sign. Okay, better. All right, now, when is the particle speeding up? All right, speeding up. We went matching signs. Here we go, matching. This whole section is matching, and one more matching here. All right, so the particle speeds up. Now I'm getting it. During the intervals -3 to -2, -1 all the way to +1, and 3 to 4, because v of t and a of t share the same sign. And then that leaves a couple that didn't get circled at all, and that's when the particle is coasting. Coasting means a 0 value of acceleration, and so that's going to be these intervals here. So the particle coasts. Doesn't matter what the velocity is doing, it matters what the acceleration is doing. So the particle coasts during the time intervals 1 to 2 and 4 to 5, and the because is that the acceleration a of t is equal to 0 during that interval. Okay, our next graph and final graph has some curves to it. It's not all just straight. So we are going to do this with exclusively pluses and minuses. We don't need to, or zeros. It's either a plus or a minus or a 0. So first I want to interpret the velocity. Okay, the velocity is just whether or not, when you're looking at a velocity graph, is the velocity graph itself above or below the x-axis. So on this interval from 0 to 1, the velocity graph itself is above the x-axis. And it remains above the x-axis for this entire section until I get to number 7. And so these are all above the x-axis. It is below the x-axis from 7 to 9, and then it returns to above the x-axis. So that's just the position of the velocity, the values of the velocity. Now I'm going to do the derivative of the velocity, or the slope of the velocity, which is what my acceleration is going to be. So now I'm going to look at the section and I'm just say, what kind of slope does it have? Not exactly the number, just is it positive or negative? So now I'm going to look at this section between 1 and 2 here, and it has positive slope. So I'm going to indicate that with a plus. I should probably use a darker color so it shows up better. Maybe the, don't like that either. How about pink? Okay, so this section has a positive slope. Now from 1 to 2, it still has positive slope, and so that would be positive again. Now after the number 2, it starts to decrease from 2 to 3, and it decreases from 3 to 4. From 4 to 5, I have 0 slope, so that's my only zero so far. And then from 5 to 6, I have 0 again. And then from 6 to 7, it is going down, curving down, so that's a negative slope. From 7 to 8, it is curving down, that's a negative slope. But from 8 to 9, it starts to curve back positive, so that's a positive slope. And from 9 to 10. So now I can compare velocity and acceleration, and I can answer a bunch of questions. So I've transferred all those values over. When does the particle change direction? Well, the only time it changes direction is from that plus to minus. So all those pluses in the velocity means that the motion of the particle is going up. And then all of a sudden it's changing at 7. And so on the graph that corresponds to this spot right here where it crossed the x-axis. There's a typo in my change to plus when I switch it over. Okay, and then it changes again from minus to plus, which corresponds to this spot. So all this whole section here means going up. And this value here going up. And the two negatives, here and here, are going down. So the particle changed direction twice. So we would say the particle changed direction, or changes direction, at t equals 7, and again at t equals 9, because the values of v of t changed sign. When is the particle going up? When is the particle going down? When is the particle stopped? So we've established that it's going up. From 0 all the way to 7, and again from 9 to 10. From that interval, the particle goes up because v of t is greater than 0. And we've established that it's going down from 7 to 9. And we established that because v of t is less than 0. And then finally, when is it stopped? And remember, the word stopped is synonymous to at rest. Don't think of stopped as like just sitting there. Stopped can be just for a moment. So it has to be stopped twice when it's changing from one to the other. The particle is stopped or at rest at t equals 7 and t equals 9, because the IVT, the intermediate value theorem, guarantees that v of t must be equal to 0 whenever v of t changes sign. All right, so because we have a continuous function, we can use the IVT. The IVT guarantees anytime there is a change in the nature that it must be equal to 0 at that position. All right, last one. And remember to fix this to a plus. Okay, when is the particle speeding up? Let's see if I can get this right this time. Speeding up and slowing down. So I'm going to do speeding up in green. Speeding up would be same sign. So I think these are the only ones. Oh, and this one. All right, so speeding up, the particle speeds up from 0 to 2, 7 to 8, 9 to 10, because v of t and a of t have the same sign. And then we'll do slowing down in red. Slowing down would be opposite sign. There's another opposite sign and a final one. So the particle slows down during those intervals because of the opposite nature. So from 2 to 4, 6 to 7, and 8 to 9, because v of t and a of t have opposite signs. And then finally the coasting, we know we can recognize that because the acceleration is equal to 0. And so that would happen on this interval here. So the particle coasts on the interval 4 to 6. And because that's the only interval where the acceleration is equal to 0. It's irrelevant what the velocity is doing, it's only relevant what the acceleration is doing. All right, so you're going to be given graphs. I think it'll be helpful in your homework if you turn those graphs into charts. Once you have your chart set, The chart will help you be able to answer a lot of questions. Charts themselves are usually not worth any points or credit on a test or a quiz or an AP question, but they are so helpful in helping you format a good answer to the question. Okay, so we'll talk about this extensively in class on Tuesday as we wrap up velocity, then the rest of lesson 2-4, and then we'll set our targets on a test for chapter 2 in October. Okay, all right, hope you have a good start to your week, because it's probably Monday that you're viewing this. So I will see you on Tuesday.